So it's a pleasure to be here. I was just on a plane from Paris last night and reflecting that these are really both France and India are two places with great traditions in probability. So it was nice to travel from one to the other. While most of the focus of these lectures will be on mixing of finite Markov chains, I decided today to start with one general estimate that applies both to finite and infinite. And then we will go back and discuss more kind of the motivation and where we will head in the rest of the course. Of course, you've seen on the website an ambitious plan. I don't promise to cover in detail all the topics there, but you'll have but I did give reference, so I will touch upon these topics and describe them to some extent, and then I included the references for those who want to see more. So without further ado, let me start with introducing what in my mind is one of the high points of Markov chains or of probability. Let me switch these pens. And this is the Varopoulos-Karn long-range estimate. So the setting will be a finite or countable a finite or a countable Markov chain. It will be reversible, so we're going to have some stationary measure pi, so that will satisfy this relation. So P is as usual, the transition kernel. So Pxy is a stochastic matrix, right? The sum for each x, when we sum over y, Pxy we get 1. And this is the equation of reversibility. So this this means reversibility with reversing measure or stationary measure pi. Now, intuitively, what reversibility means is that if you observe the Markov chain and then think of it as a movie where you see the Markov chain moving, then you take this movie and you run it backward. If you started at stationarity, so x0 is chosen according to pi, then you cannot tell when looking at this movie if you're seeing it forward or backward. So maybe before going in, let's just recall. So the standard, so one basic class of examples are simple random walks on graphs. So we start with G, a finite or infinite graph. All the degrees will be finite, so every vertex has finitely many neighbors. And the transition probability Pxy is just 1 over the degree of x if y is a neighbor of x. So I write y tilde x just to mean that y is a neighbor of x in the graph, and 0 otherwise. Right? So that's simple random walk. And simple random walk is always reversible where pi of x is the degree of x. So notice this is a measure on the vertices of the graph or the states of the Markov chain. As you can see, it's not normalized. So this pi, when we sum it over all nodes, we will get something large in a finite graph and an infinite value in an infinite graph. If we're working with a finite graph, it's often convenient, and we often will normalize pi. Of course, when you normalize, that doesn't change this equation. So with this setting, we can... Okay, so that's the example of a reversible chain. Now, more generally, instead of simple random walk on the graph, you can start with a... So if you have a graph, you could have weights on the edges of the graph. And these are often called conductances. So for every edge, you have a weight. And then instead of simple random walk, where all edges have the same weight, you give each edge the weight which is this conductance. So given at the vertex, you choose which edge to walk on proportional to these weights. So the probability to take an edge E is the conductance on E divided by the total conductance from the node. So those who haven't seen this may want to verify that this is already full generality. That is, if you have any irreducible reversible Markov chain, then you can represent it by a random walk on a weighted graph. So these are just two views of the same object. To go in one direction, if you have a weighted graph, pi of a vertex will be just the sum of the conductances on the edges from that vertex, right? So pi of x you take to be the sum over all edges E of the form x something, and CE. So just the total conductance on edges coming out of x. So, and that will be the stationary measure with respect to this weighted walk. Remember, the probability of choosing in going along an edge E will just be CE divided by pi x if we start at x. So this is random walk on a weighted graph. It's an example of a reversible Markov chain, but in fact it's the general example. And irreducibility of the reversible chain corresponds to connectedness of this graph. What's an example of a non-reversible chain? Well, this you can easily draw many, but the most important for us will just be a biased walk on the cycle. So, for instance, suppose you walk with probability 2/3 to the right, say 2/3 clockwise and 1/3 anti-clockwise on a cycle. This is a very nice irreducible Markov chain, and the same rule from every vertex, probability 2/3 to the right, 1/3 to the left, or 2/3 clockwise, 1/3 anti-clockwise, and this chain is not reversible. So you can't put pi there that will satisfy the reversibility equation. And indeed, if you look, if there was such a pi, it would have to double each time you go in this direction, and of course that can't work when you close the cycle. So note there's a big contrast. If I compare this to this chain, suppose I have a path, and every vertex I walk probability 2/3 to the right, 1/3 to the left, and let's make this node absorbing. Well, this maybe we won't make it absorbing. We'll make it from this node you go just to the left, from this node you go just to the right. So suppose I make a small modification of the cycle by just really removing one edge from the cycle or breaking one edge. Then I get a path, and at every vertex I walk probability 2/3 to the right, 1/3 to the left. But at the endpoints I can't do that. So at the endpoint, say you automatically go to the neighboring node. This is still an irreducible Markov chain, and this one is reversible. So these two chains behave completely differently. They only differ by one edge, but completely different. Here, the walk is the stationary. There is a stationary measure here. So stationary measure, recall, is just the relation pi p equals pi. If I think of pi as a row vector and p as a matrix, this is the stationarity. So in this case, the stationary measure is just uniform. It's a unique stationary measure, and it's uniform measure. Unique up to scaling, of course, always. If you want probability measure, then it's really unique. But in this case, the stationary measure is completely different. Here it's uniform, and it's not a uniform stationary measure, and it's not reversible. Here, pi will grow exponentially. Each time you go from one node to the right, the endpoints are a little bit different, but inside, the mass keeps doubling. And so almost all the mass of the stationary measure will be concentrated on the right-hand side. So one thing you might want to think about is, if you haven't, so this one is not reversible, and it's clear if you look at the movie, if you look at this chain, well, it typically is moving to the right. So of course, if you reverse the movie, it will look differently. But it's a little bit surprising the first time you see this. I said this chain is reversible because you can easily write pi that will satisfy the reversibility equation. But here it also seems like the chain is typically going to the right. So but I told you that reversible chain means that if I look at the chain, I can't tell if I'm looking at going forward or backward. Who can tell me what is? So it looks like a contradiction. I'm telling you that this chain is reversible, but if I look at it, it seems like it should be moving typically to the right. What's the solution of this paradox? We're starting at stationarity, thank you. And because the stationary measure is so concentrated near here, when I run at stationarity, I'm basically always running near here, constantly banging into this right endpoint. And so you really cannot tell that's true both for the chain and its reversal. But there's still something a little non-intuitive here, so you may want to consider it a bit. Okay, so with that background, what is the estimate that's in the title there? So the theorem, the Verblunsky theorem, it says that for a reversible, so in the setting I mentioned, the transition probability pt of xy. So this is a transition probability in t steps, or equivalently, this is just entry in the matrix p to the t. But we think of it probabilistically. It's the probability to go in t steps from x to y. Okay, it's bounded by twice there's a factor pi y over pi x times the probability of st. I'll explain what this means, bigger than dxy. And this in turn is bounded by 2 root pi y over pi x e to the minus d squared of xy over 2t. Okay, so where st is, maybe I'll write p0. St is simple random walk on the integers. Right, so our most basic Markov chain is on the set of integers, which walks one step to the right, one step to the left, equally likely. That's st. So now I'm using t to index time, although time for me will usually be discrete. So just be aware that t is, going through the integers. Why are we not using n? Because often we will have finite graphs with n nodes, or anyway, n will be a parameter relating to the size of the finite graph. So I want to use something different from time, so it will be t. Good. So dxy is the distance from x to y in the graph determined by P. So I told you before how to build a Markov chain from a graph, but we of course can do it the other way. Given a Markov chain, we define a graph where two nodes are adjacent if we can move from one to the other with positive probability. And because we are talking about reversible chains, this is an undirected graph, right? So if I can move from x to y, I can also move from y to x. Of course, you can build such graphs for general Markov chains, then they will be directed graphs. Okay, so this is an undirected graph, and we're just measuring distance in this graph. In other words, dxy is the minimal number of steps that the chain needs to go from x to y, or equivalently from y to x. Okay, so it's a distance.
The weight is 1?
What?
The weight on the edges, you take it to be 1?
No. So this is a general... So the weight is not playing a role in this formulation, but really I have a general Markov chain P. So if I want to think of it as a weighted graph, then I would use the conductance I would use on an edge xy would be, for instance, pi of x times p of xy. If you want to think of it as a weighted graph, well, this solves the exercise I asked before to show that any reversible Markov chain is obtained from some weighted graph. So these are the weights that will give this that will correspond to the Markov chain. But notice that in the formulation of the theorem, the weights don't appear. We just have p and pi and the graph. But the weights on the edges, well, they are implicit, but they're not explicit there. Any questions about the statement, what it means? So, yes? I can't hear. Yes, that's why I said setting, which is reversible Markov chain. Yes, definitely. Okay. Any other question? So, right. Just to get our bearings, so I mentioned reversible Markov chain. Let's look at this non-reversible example. We have n vertices. Suppose I take t, which equals, just let's test this theorem in this example, which is not reversible. So suppose I take x here and I take a y here, and let's take the distance from x to y to be, say, n over 3. So, and take time, which is n. Okay, so notice that this Markov chain is just the projection to the cycle of a biased walk on the integers. A biased walk on the integers walks, right, which walks with probability 2/3 to the right, 1/3 to the left, has a drift of 1/3 to the right. So just from the the law of large numbers tells you that at time t equals n, the walk is expected location is going to be about n over 3. And the central limit theorem, or more precisely the local central limit theorem, tells you that the probability to move from x to y in this example, where their distance is n over 3, the probability is approximately what? So you should be able to tell me up to constant. The constants involve some pi, and I don't care about them now. But what is the probability if x and y are distance n over 3, and I move and I take time, which is n, and this is, say, an n cycle? What is the chance to go from x to y? What is the order of magnitude of this probability? Okay. Yes? So the Verblunsky bound would give an exponentially small probability, but no, it doesn't apply because this chain is not reversible. So I'm asking, this example is really contrasting with the theorem. It's not an example of the theorem, it's an example where the theorem doesn't apply. It's an example where the probability here is much larger. So the mean of the walk after n steps is n over 3. So if I was doing it on z, the mean would be n over 3. The variance would also be order n. Again, I don't care now about the constants. So it means the standard deviation is root n. And a walk after n steps would be distributed around n over 3 with a standard deviation of order root n. So the probability it will land exactly at n over 3 is going to be constant over root n. And this is much, if you try to plug in these numbers, you'll get, as was commented here, you'll get something exponentially small. So you see the Verblunsky bound gives you something which, it actually turns out to be a remarkably strong bound. And this example is just to illustrate that it doesn't apply without reversibility. So we're really using reversibility. So, okay, so let's see, where is this the eraser? Yeah. So the content, the real content of the bound is the first step. The last step is just the classical large deviation bound for the binomial that goes under many names. Maybe Bernstein was the first to prove it, but you can find it under Chernoff, also under the name Chernoff bound. So let's just warm up with this statement. This is something, which is about close to 100 years old now. The bound on just a simple random walk on Z. So right, so I have so when t and r are positive numbers, the probability that st is bigger than r is bounded by, has a kind of Gaussian tail. So, so this is a special case of much more general estimates, but let's just do this one. So let's take x, which is the basic increment of the simple random walk. So it's plus minus 1 with equal probability. So expectation e to the lambda x, so the moment generating function is just e to the lambda plus e to the minus lambda over 2. So it's just a hyperbolic cosine, but let's write the Taylor series of this. So it's just some, we only have the even powers here, right? Because the odd powers cancel, and we get lambda to the 2k over 2k factorial. So just the even part of the series for the exponential, k from 0 to infinity. And observe that this is less than the sum over the same range of lambda to the 2k over 2 to the k factorial. So if you look at 2k factorial, right, it's a product of all the numbers until 2k, but if you just take the even numbers until 2k, you'll get, so this is a product of t independent factors, so this will just be e to the t lambda squared over 2, because it's going to be the tth power of this expectation. Okay? So now we're going to use that with Markov's inequality to bound less or equal, thank you. So we're going to use that to bound the probability of st bigger than r, which is of course the same. T and r are positive, T and r are both positive numbers here. So this is the same as the probability of e to the e to the lambda st being bigger than e to the lambda r. And now Markov's inequality allows us to bound this by e to the minus lambda r times the expectation of this quantity, and the expectation we already bounded by e to the t lambda squared over 2. Okay, so this is just Markov's inequality. And so this bound is true, and note this doesn't involve lambda. Here there is lambda, so we can choose whichever lambda we want, and of course we optimize. So to optimize this, this is just the exponential of some quadratic function of lambda. So to optimize this, you just choose the lambda that well minimizes what's in the power here. So what lambda is that? Sorry, r by t. So if you choose lambda, which is r over t, then you'll get exactly this bound. Okay, so that's the Chernoff bound or Bernstein bound. And again, there are many fancier inequalities, but often the starting point is a similar calculation, which is then done in a more refined way. Okay, so that's the. So observe that, of course, this is reminiscent of the central limit theorem. The difference is that there are no root to pi here, no integrals, and it's not an asymptotic statement, it's a bound. This bound is quite good as long as r is not too large. But observe, if you take r equals 2t, the probability is 0 there on the left, and the right-hand side is some positive quantity. So this bound, is not always optimal, but in many ranges it's quite useful. All right, so that does the easy part here, and so Veropoulos and Karn were not doing this; they were doing this. In fact, Veropoulos proved a weaker inequality by a kind of amazing method. So what did Veropoulos do? He had this graph where he wanted to prove this inequality, and he didn't know how to do this directly in the graph, but he was an expert on Brownian motion and manifolds, and he realized that he could take the graph, replace every edge by a little pipe, and create a manifold which behaves a lot like the graph. So think of replacing every edge by a pipe, you get some surface which is constructed of all these pipes, and it was already known, this goes back to work of Furstenberg and Kanai and others, that Brownian motion on this manifold is a very good approximation to random walk on the original graph. And he was able to use this connection together with some tricks from PDE or Brownian motion on manifolds to get a bound of this nature, although he had some additional factors, so it wasn't quite as elegant as the one I write here. So this was in 1985, and shortly thereafter Keith Karn in England found what is the right discrete analog of the Veropoulos proof. And this proof is one of the really gems of probability, or use of basic analysis in probability. So I want to show it to you now. So I said the basic idea of this general idea is due to Veropoulos. The exact theorem, as I stated there, is due to Karn. And I gave some references in the notes. So let's prove it. But we're going to simplify our life a little. We're going to prove it in the case where pi is uniform. So this is the case where P is just a symmetric matrix. And it's a good exercise to generalize the proof I show you here to the case of a general pi. And if you get lazy with this exercise, you can find it in Karn's original paper or in the two other sources I gave in the notes. So in my book, there's an exposition in my book with Russ Lyons, and there's an exposition in the notes with Julie Komyathi from a similar school I gave in St. Petersburg a few years ago. But on the board, I'm just going to choose the lazy route myself and just do it with pi uniform. That is really only a notational saving, but we'll do that. So let's go. We're going to prove it in that case. So then we don't have this little factor with this square root and this statement, and it still applies to lots of cases. So random walks on regular graphs. So if you have a graph where all degrees are the same, then pi is uniform. And actually, Veropoulos-Karn theorem has had some of its most spectacular uses for random walks on groups, which are regular. So this is already an important case. It's not just a trivial special case. Okay, so let's prove it in that case. So the proof won't be long, but it will look a bit like a miracle. So hold on. It uses the Chebyshev polynomials, but luckily it doesn't require any knowledge of fine properties of the Chebyshev polynomials, just their definition. So let's where did it put it? Okay, so I'm going to call them QK. Usually they're called TK, but I'm going to call them QK. And QK of cosine theta is cosine of k theta. Now again, I'm not going to assume you know anything about these polynomials, so I'm going to, because what we need about them are very easy things we will derive right here. So first, in particular, we will see why these are polynomials. So let's do the easy cases. So Q0, so if k equals 0, Q0 is just identically 1. And Q1, well, Q1 of cosine theta is, so Q1 of a variable, maybe we'll call the variable z. Q1 of z is just z. Okay. Who's close enough to high school to remember what is Q2?
2z squared minus 1.
Thank you. 2z squared minus 1. Now, in general, there is a recursion for the Chebyshev polynomials, and it's obtained from the trigonometric identity if you add cosine k theta and cosine k plus 1 theta and cosine k minus 1 theta, you'll get twice cosine theta times cosine k theta. So if we use this, right, so here I mean this is the cosine of k plus 1 theta. I'm not putting in all the parentheses I really need to. And this is the cosine of k minus 1 theta. So in terms of, so this is just so if we think of, so again, we denote z as cosine theta for the moment. Then this is saying that qk plus 1 of z plus qk minus 1 of z equals 2z qk of z. Okay, and this proves by induction that the qk indeed are polynomials. So qk is a polynomial with degree k. You just get that by induction, so we saw it for 0, 1, and even 2, and then for larger k, if you know it already up to k, so you know that this qk is a degree k polynomial, then here you're getting something of degree k plus 1. You have to subtract something of degree k minus 1, so you'll get something indeed of degree k plus 1 for qk plus 1. So this is these are the Chebyshev polynomials. So what do we need about them? We need that we'll use a couple of things that will be easy to derive. So, but one key thing I want to point out now is that if z is a real number between minus 1 and 1, then qk of z is also a real number between minus 1 and 1. So note qk, I defined it this way, but of course now that there are polynomials, I could plug in any z I like. I will only, despite the notation z, I will only plug in actually real z for this, but later it will be I will replace z by a matrix. But I mean, given a polynomial, you can plug in anything that you can take powers of, you can plug into a polynomial. But if z is between minus 1 and 1, then z can be represented as cosine theta, and then because of the original definition, we know that qk of z is also between minus 1 and 1. If you write these out as polynomials, well, for q2 it's still obvious, but if I write q15 and I look at this polynomial, it's not clear from the expression that it's bounded between minus 1 and 1 in the interval minus 1, 1. But it is clear from the original definition. Okay? So that's one thing we'll use. By the way, if I'm going too slow or too fast, please let me know and I will try to adjust. So. Just one more. Okay. So this is what we still need to prove, so I'll try to keep that on the board. Okay, so the other thing we need is a consequence of the binomial expansion. What happens if you take cosine theta to the t-th power? So I want to write this in this form, take this to the t-th power, and now we can write the binomial expression, and I claim what we get when we write it out, I can write in the following way: the probability that st equals k e to the so k here ranges from minus t until t. So of course, if you write the binomial formula by definition, it will look a little bit different, but then you can rewrite it in this form. Another way to think about it is that if you just really literally think of you have all these factors, e to the they're plus e to the minus I theta, over 2, and I write this power by writing t factors like that, and now I have to multiply this whole thing. Well, in order to multiply, I just have to select one of the summands here, one of the summands here, and so on. So I just have to select these summands. And this selection is exactly the same as the selection that a random walk has to do, going left or right. And in the end, if I selected j times to go j times to go left and k minus j times to go right, I will t minus j steps to go right. I will end at some location k, which is t minus 2j, and you see that the coefficient of e to the ik theta here will be exactly the total probability that the random walk will be k. Anyway, this is just taking the binomial formula and rewriting the indices. So I'm going to leave it at that. But let's see what that means in terms of the Chebyshev polynomials. First, let's take real part of both sides. After all, the left side is real. So and in the right side, so if I take real part, so the right side is real, although it's not as apparent. So if I take real part, it's not going to change, and it's going to be the sum over k of the probability st equals k, and the real part of e to the ik theta is the cosine of k theta. I'm sorry, I have cosine t to the t, thank you. Okay, so now if we use the same notation from the other board, z equals cosine t, we'll get the z to the t equals the sum over k from minus t to t. Probability that st equals k, remember st is the simple random walk, started at 0, times qk of z. This is an identity. Now, I should be more careful here. I want to write q absolute value k. So here I have a sum with both positive and negative values, but of course cosine k theta is the same if I change k to minus k. So, and the polynomials are only defined for positive index, so I put q absolute value. Okay, so we have this identity. This is an identity between polynomials, right? Z to the t can be written as a sum of Chebyshev polynomials with these binomial coefficients in front. Questions? Okay, so if we have an identity between two polynomials, I mean, we verified the identity when z is cosine theta, but if two polynomials are equal on the interval -1, 1, they're really equal. So these polynomials are the same polynomial. So I can plug in, instead of z, which is the variable in this here, I'm going to plug in the matrix P, the transition matrix P. After all, P, I can take powers of it, and I can add, add powers. So, so we get it's dangerous to mix these erasers. So somehow someone couldn't decide if they wanted the whiteboard or a blackboard, and it looks like the decision by committee. Okay, so all right, so let's plug in the matrix P. So P to the T is the sum probability. You see, I mean, we want to prove something about an entry in P to the T. So right now I've been telling you about polynomials. It seems completely, what am I doing? What does it have to do? Finally, well, there's at least going to be some P to the T in the game. So P to the T. So this is the matrix P, and here this kind of blackboard bold P, this is the probability for simple random walk. ST equals K times Q absolute value K of the matrix P. Okay, so this is the same identity, but when the variable has been replaced by a matrix. Okay, so this is an identity between, well, polynomials, but now it's polynomials and matrices. So now it's an identity between these two matrices. And we're going to look at really what we want is to look at the specific entry on the left-hand side. So we want to understand what can we say about the entries of the right-hand side. So let's focus, so this is some combination here. So let's focus on these QK of P. What can we say about them? So first thing is, if the distance from x to y is bigger than k, then let's look at QK of P. Okay, let me think of positive k. Suppose that the distance from x to y is actually strictly bigger than k. What can we say about this matrix entry? You take QK of P and look at the matrix entry at xy. It has a very round value. Yes. What is the value? It's 0. Why is it 0? Remember, QK is a polynomial of degree k. So it's a combination of powers p, p squared, p cubed, up to p to the k. But if you look at a power like that, for instance, p to the k xy, it is 0 because the distance of xy is the minimal number of steps you need to go from x to y. So by definition, if k is less than the distance, p to the k xy is 0. You cannot go from x to y in k steps. They're just too far. Okay? So all of these entries when the distance is bigger than k are 0. Now we also have to say something about other entries. So if we don't have that condition, what can we say in this case about QK of P of xy? And I want to write it in kind of a vector notation. This is the, if I take the unit vector at x, so delta x is a vector which is 1 at x and 0 everywhere else, and I can actually write this as a scalar product of delta x times QK of P applied to delta y. So this is this is the point where when we have a general reversible chain, we have to take the scalar product in L2 of pi. But here we're just taking a standard scalar product. So I claim that we can bound this rather effectively. So to bound it, if I have a matrix and I take, apply a matrix to a vector, I can bound this by the norm of the matrix. And because my matrices here are symmetric, P, remember we're doing the case where P is a symmetric matrix. So all the powers of P are also symmetric. And any polynomial in P is also a symmetric matrix. So QK of P is a symmetric matrix. So for a symmetric matrix, what do you know about its L2 norm? How much its operator norm? It's given by the largest eigenvalue. Thank you. So really to understand how big this quantity could be, we have to understand how big is the largest eigenvalue of QK of P? How big can it be? Now, what are the eigenvalues of QK of P? Well, we don't know, but we can say in terms of the eigenvalues of P. So if lambda is an eigenvalue of P, what are the eigenvalue corresponding QK of lambda, right? You diagonalize P, and then, when you're taking powers, the diagonal form evolves. So again, this is recalling some linear algebra. We know that right, so the eigenvalues of QK of P all have the form QK of lambda, where lambda is an eigenvalue of P. Now P is a symmetric matrix, so all its eigenvalues are real, but P is also a transition matrix for a Markov chain. So all its eigenvalues are between -1 and 1. The largest one eigenvalue is 1. So all these lambdas are between -1 and 1. By the way, maybe when we finish the proof, we'll ask one of you to recall the proof, why all the eigenvalues of a Markov chain are in absolute value at most 1. But anyway, that's an easy fact. We're after the break. We're almost there. Okay, so lambda is between -1 and 1. So QK of lambda is also between -1 and 1. So this is what I discussed before, that the Chebyshev polynomials map -1, 1 to -1, 1 because of the definition. Cosine k theta is also in -1, 1. So this means that P, its operator norm is at most 1. So this QK of P delta y has L2 norm at most 1. And so this whole thing is at most 1. In absolute value. Okay, so now let's go to the identity we have here and plug into that identity a particular entry. So we're looking at P to the T at the entry xy, and we have sum over k. Now, the k, as we discussed, we only need to take k, which is an absolute value bigger than the distance from x to y. The smaller k give us a contribution of 0. And for these k, again, now I'm going to write an inequality. I don't need an absolute value because this thing is positive, but it's not going to kill me. And so I have a sum over k's so that the absolute value of k is bigger than dxy. And then for those, I have to take qkp and look at the xy entry. And we said that's at most 1 using this kind of spectral argument. So we have the probability of st equals k. All right? And in the case when pi is uniform, this is exactly what's written here. Right? It's the probability that st is bigger than dxy, and there's a factor 2 here because we have this absolute value. Okay? This is exactly what was claimed. So as Manju indicated, this is a good time for a break, so we'll stop.